So welcome back, and I'm Stephen Forbes, and Chipmaster, and in this class we're going to learn about EC and BIOS. Okay, alright, so I have here a presentation of the content that I'm going to explain, right? And it's the EC, right, which is the embedded controller, is a single chip or a microcontroller or a microcomputer. So architecturally, the EC does the same role as for the desktop machines, right? Input, output, but the function is more powerful, much more powerful than the desktop, right? So when the system is turned on, the EC controls the timing of most of the important signals, right? In the shutdown state, the EC keeps running. This is when you plug in the adapter or the main battery, right? The EC gets its working conditions and then it will start working, right? And it awaits for the user's power on instruction. Right, so after booting, the EC controls various indicators, right, such as the LED indicators, the hard drive LED indicators, the charging indicators, and so forth, the fans and other devices such as your audio, right, the keyboard, and so forth. It also manages the charging. It can also manages the temperature of the entire system. All of the temperature information, the thermal information is passed through most time an SM bus, which is connected to the EC. And as I said, it controls the fan and many other devices, right? It even controls the system standby hibernation and other states, right? The EC generally contains a keyboard controller, so it is often called the KBC, right? So that is another name that most persons call the EC, which is the SIO. Some people call it the EC, some people call it the KBC, some people call it the microcontroller. But for a typical ordinary engineer, maintenance technician, we normally call it the EC. Okay? Alright, so I have here common EC types and manufacturers. As you can see, we have here Winbond, right, which is a common manufacturer, right? Now mostly for manufacturing BIOS chips. We're not seeing them manufacturing a lot of ECs for the newer architecture machines. They are mostly found on the EC in the BIOS region. Right. We also have ITE. Right. So we have the ITE QFN package, and we also have the BJ package. Right. So as you can see, we have ITE, which starts with an IT. So each ITE chipsets or EC always starts with IT. Right. IT 8586. IT 8512E, IT 8572G, right? Normally when it's ended a G, that means it's a BJ package, right? Most of the ITE series ECs ending with G is most times a BJ package. These are QFN, which stands for, these are TSOP packages, right? And these have leads protruding outwards, and these are BGA, right? And these are common types of EC, right? Lenovo, this is mostly found on the Lenovo machines, such as the Lenovo IdeaPads, right? And these are found on those Lenovo machines, right? But it's still manufactured by ITE because it begins with IT. We also have SMC, SMSC, which is normally found on the newer Dells, Latitudes, and this is our powerful EC. We also have ENE, which is the KB9012, and we have Nuvoton, which is another popular manufacturer of ECs. So all these SMCs, all these ECs manufacturers are what we commonly see on daily basis during the maintenance of the motherboard, and these EC are what are now in the trend for the manufacturer. Okay. We also have the BJ package, as I said before. These are found on the Apple machines, such as this one, the LM4 S1 BH. This is a BJ package. All of these are BJ package ECs, right? And they are found on both PCs and Apple laptops. Alright, so we're going to move on to the BIOS. So the BIOS is the basic input output system, which is a group of programs that is solidified on a ROM, right? Which is a ROM, which stands for read-only memory chip on the motherboard. It is now habitually called the ROM chip with the solidified program. So the program which is stored on this chip and it's located on the motherboard, right? It is a very important and crucial part of the motherboard, the BIOS, right? So the BIOS is connected to the PCH or it's connected to the EC, right? So the EC needs to get its program in order to read it to configure, right? So the EC BIOS and the main BIOS are two different BIOS. One for the BIOSes are work independently depending on its function, right? So many problems in the system, this is a typo, can be corrected through the BIOS, right, program. The continuous update of the BIOS reflects the ability of the motherboard manufacturer. If it does not modify or upgrade the BIOS for a long time, it is likely to be a manufacturer without certain capabilities. So when buying a machine, buy those machines that frequently upgrade their BIOS. So that is a very important, because the BIOS basically fixes certain bugs, right? So if a manufacturer releases a motherboard and it has a bug, a BIOS upgrade will fix the problem and correct it, as it has said before here. It's just corrected through the BIOS, right? So if the BIOS is not upgraded for a long time, then there's a lot of flaws and a lot of bugs that needs to be corrected, and that's very important to have regular upgrade of a BIOS, especially for the gaming machines. Okay, right, so BIOS chips of the motherboards are now 8 pins, right? The BIOS contains the most important computer self-check program and interrupt service program. It also reads and writes specific information about the system settings, modification time, etc. For the CMOS, its main function is to provide the lowest and the most direct hardware settings and control for the computer, and this is where the CMOS comes into play, right? So the CMOS, which stands for complementary metal oxide semiconductor, and it is used to store these settings for the hardware, as it says, lowest direct hardware communication, right, and date and time, which is stored in the BIOS and under the CMOS. Alright, let's now look at the EC's basic working conditions. Some of the standby, the EC has a set of working conditions. In order for it to work, it has to go through a set of working conditions, right? And here I have them, which is the first one, which is the standby power supply, and this is normally 3.3 volts, which is a common standby names for this 3.3 volt. We have AVCC, we have VCCO, VCC1, VCCA, VSTBY, and VBAT. Right, these are the common standby names that we use. So let me just get a schematic here. Head over to the schematic, as I have a schematic here. Let's start off with this one. Right, so I'm just gonna type AVCC. I already typed it. So AVCC. All right. AVCC. Let me try again. AVCC. AVCC. Oh, here it is. So AVCC, as you can see, this is an EC, and the common EC is a common EC. As you can see, it's a KB9012QF. Right, so the common name for the EC, the standby name, which is AVCC, and this is pin 67. So this is an ENE. Right, ENE normally starts with KB. As you can see, let me go back to the previous slide. Alright, so ENE, which is a common name for the starting, which is KB. All ENE EC starts with KB and then the numbers after it. Okay, so that's a common the EC name. Okay, so this is an ENE. As you can see, its standby power supply name is AVCC. We also have VDD-VCC, which is also another power supply pin, standby power supply pin, right? And that's for the ENE. Let's go over to another one here. Let me an AVCC search again. Okay, we have AVCC here. Alright, this is another common supply name. We have VCC1, VCC2, VCC3, which is another standby name, and this is a WinBond. As you can see, WPCE775L, so WINB, which stands for WinBond. And this is another common for older machines. We have here the standby name, which is AVCC. So if you want to quickly get to the EC on the schematic at any page, you just simply type in AVCC. Right, we also have another one here. Let me search for AVCC. Oops. And this one, AVCC. No, that's not it. 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 ABCC. So this one most likely has a different name. Alright. So there is no ABCC here. So we can try the other one, which is VCC1. Does it have it? We have a VCC1. Yes, this is a power supply for the RTC section. VCC power good. Alright, so here we have another page here, and this is a KBC 1070. Alright, as you can see, VCC power good. This is the RSM reset pin. So VCC, this one doesn't have ABCC. Right, normally this starts with VBAT or VCC1, VCC2. This is the standby name. So as I go back to the presentation, we have ABCC, we have VCC0, we have VCC1. Alright, so this one uses VCC1. So VCC1, all of these are the standby name, and we have VCC2. Right, this is another standby name, VCC2, VCC1. Right, so depending on the manufacturer of the IC, each manufacturer name is different. So this is KBC, so this is an SMSC, right, brand. See, SMSC 1070 EC. Right, this is an older brand model. Okay, so EC, let me pause. All right, so here we have an Apple. All right, so let's type in ABCC, see what we get, and I found nothing. Right, so ABCC, so this is a different architecture. This is a different EC. This is an SMC. Let's type in VBAT, and here we go, VBAT. That's not it. Nope. VBAT VDD, and here is it. So this is a SMC. You see, LM4SH U49 and VBAT, which is a power supply standby name for this EC. So each manufacturer of EC has a different name for their standby names. Okay, so as you have, as back to the back to the standby name. So we have ABCC, VCC0, VCC1, VCCA, VSTBY, and VBAT. Right, so these are the common names. So you can search for each of these names if you're not sure of the manufacturer's standby common power supply name, and you can find it, and immediately you will find it. And these are normally 3.3 volts. The next working condition, which is a standby clock. Right, so in older machines there is a crystal which provides a 32.768 clock. Right, but newer machines now have the clock integrated inside of the EC. Right, so this is the new architecture design. So there's no crystal on the external side of the EC, just like this one. As you can see here, I have here a EC. This is the EC. Right, this is the EC, and we have a crystal here which is going to provide 32.768 kilohertz to the EC. Right, and this is basically using a crystal to provide its clock. So newer machines don't have a crystal. Right, the crystal is now removed, and it's being used to, it is using a different architecture, which there is no clock crystal. It's integrated inside of the EC, such as the KB9012. Let's go back to the schematic, and let's go for this one. Right, as you can see, there is normally a crystal which is connected to it. Right, so here are the clock pins: X clock, GPIO 5D, and we have X clocks input, and we have X clock output. And you can see it is connected to sus clock, and this normally comes from the PCH. There is no external clock, so the clock is integrated inside of the EC. Let's go to this one. Let's see if we can find a crystal symbol, and it's normally on this side. Here is it. So we have 32.768, as you can see. Right, and this is a crystal, and the crystal is connected to its resonance capacitance, and as you can see, 32k x1, and that's going to the EC. Right, so let's copy that signal, and as you can see here, it's connected to pin 77 of the EC and pin 79, X1, X2. So this EC does has an external clock crystal. So this is an older machine, as you can see. So newer machines don't have a crystal. The crystal is integrated inside of the EC, such as the KB9012 or the KB9022 and so forth, and IT85. All of the newer models now has their clock integrated. Right, now we have the next one, which is standby reset. Yeah, the EC's initial reset signal. Right, common names are like ECRST, WRST, VCC-POR, VCC1 underscore power good, and RES, and VCC1 underscore RST, sorry. Right, some EC have an internal reset. So going back to the schematic, as you can see here, common EC names are ECRST. Let's search. Nope. Let's type in EC underscore RST. Nope. Let's type in VCC underscore PWRGD. No. So as you can see, you have to know the name of each manufacturer of the EC of the reset pin. And let's take a look. So this is an older EC. As you can see, this is Winbond. Alright, PCE 775L, and I'm going to search for the EC reset, the reset pin of this initial reset pin of the EC. Alright, so we have supply. Right, we have a reset here. This is for the LPC bus. We have EC power switch, which is the main switch. We have RSM reset, VCC-POR. As you can see, here is the reset signal, right, and it is VCC-POR, and it is connected to pin 85. Right, so as you can see, we have VCC-POR here, which is the another common EC reset name. Right, so this is this is the reset name for this EC. Let's go over to the next schematic, and let's type in the first one again, ECRST. All right, didn't find anything. Let's type EC underscore RST. All right, yes, and we found something here. As you can see, this is the initial reset pin, which is EC underscore RST hash. As you can see, it's connected to a 3-volt always supplied through a resistor and a capacitor, and this is known as you know, this is an R, right, C delay, right, so this is a resistor capacitance. So the resistance, right, multiplied by the capacitance. Right, so this is normally connected to a RC delay circuit, and most times it is connected to the shutdown, the thermal shutdown signal. So if there's any over temperature that occurs on the laptop, it will pull this signal low. When EC signal is pulled low, then the standby voltage will be pulled low, which is 3 volt and 5 volt, and RSM reset will be pulled low, indicating that there is a over temperature problem. Okay, so EC standby reset, which is the initial reset signal, and these are the common naming for the EC. Right, we have the program, which is the EC needs to read its program in order to configure its GPIO pins. Right, so as you can see, GPIO stands for general purpose input output. Right, so every manufacturer of an embedded controller can operate in different ways depending on the design of the motherboard. So let's say you have a particular pin that acts as an input on a Quanta board. It can act as an output on a Wistron board, but it's the same brand, manufacturer, and even the same model of the EC. So the program basically gives the EC a set of instructions how to use these pins either as an input or as an output, and to do specific functions. Right, so if the program is abnormal or the program is corrupted, then they cannot turn on the machine. Right, but for like the AVCC pins, right, you have EC reset pin, right, supply reset, there's integrated clock. If you notice, there's no GPIO pins beside it. If you look at these other pins, you see GPIO 3, GPIO 4, GPIO A, B, C, D. All these are defined by the program. Right, GPIO, see, GPIO, all these signals are defined by its program. It has an input, it's an output. See, we have incoming signals, we have outgoing signals. So the program, which is the internal program, which is connected to the flash ROM, as you can see, this doesn't use a flash ROM because the signals are used for different functions. As you can see, we have for the optical disk drive, we have Bluetooth, LED, HDD, S3. So it's a different function and it's all configured in the program, right? But the main standby pins doesn't need a program because this is fixed, this is not changed. So it needs supply, it needs a reset. So there's no GPIO pins which is connected to it. Once it gets supply, reset, and the internal clock, and reads the software, then it's going to configure these pins to work depending on the software, the program that is giving it instructions. It will now configure the GPIO pins, which is general purpose input output pins. Okay, so that is why the program, right, is important. Some EC programs are stored in a RAM chip, some are embedded in the EC. For example, the KB9012 IT8586E, right? And as you know, these programs are very important for the EC to configure the GPIO pins. Okay, and these are the main basic working conditions of the EC, right? Supply, clock, reset, and program, right? So as I said before, if the program is corrupted, then you cannot turn on the machine. It's in a dead state because the EC doesn't know what to do. So if you press the switch, it doesn't know what signal that is coming in. If it's an input, what should it do after getting the input of that power down of that switch signal, right? It doesn't know. So the program basically configures that pin for it to do that specific function, that when you press the button, it accepts that and indicates that it's a turn on signal. Then it will send the power button to the PCH to turn on the ACPI configuration signals, right, which is your sleep signals such as SLPS4, SLPS5, SLPS3, right, to go into the different states. Okay, alright, so as I said before, this is the physical appearance of an EC and BIOS in the circuit. So we have a crystal, we have a BIOS here. Alright, this is the main BIOS, this is the BIOS. This is an older model, so most times the system BIOS and the EC BIOS is integrated in one chip. So one side for the EC, right, and the other side, right, which is for the CPU to read, to find the soft straps, to start the self-test information, to self-check each devices, right? So this is an older model. Okay, so this is the architecture of an older model motherboard, where the EC and the crystal and the BIOS is connected, right? Alright, so let's move to the next slide. Alright, so the EC and BIOS architecture. So the EC needs to complete various tasks and it needs to be configured by the program, which is the ECROM. Alright, the program may be stored in its in its internal ROM, or may be stored in the motherboard's BIOS. Others, on newer models, EC has embedded ROM. So how to judge that the EC uses a ROM or it uses its own embedded program? Right, so the EC is connected to the PCH by the LPC bus and the SPI bus. That means the EC has no built-in program. Some motherboards has two ROM chips, one for the main BIOS and the other for the EC BIOS. Right, so there are different architectures for connecting EC and BIOS, and how the chipsets, the PCH or the CPU will read the BIOS. Either it's going to go through the EC or it's going to go through the SPI bus directly to read the BIOS. So as you see, let's go to the block diagram of this chip, of this schematic, sorry. Alright, let's go to the block diagram. As you can see, we have a CPU here, which is the Intel Ivy Bridge, right? This is a third generation of Intel series CPU, right? And we have here an Panther Point, which is the HM76, right? As you can see, down here we have two BIOS chips, which is a SPI ROM chip, and we have another SPI. So this is for the main BIOS and this is normally for the ME firmware. As you can see, this is the EC and it is connected to the PCH via LPC bus, and therefore if you notice the EC is managing the keyboard, it is managing the touchpad. That's it. Normally you'll see another path here, for example another path here. If it doesn't have its own program, you'll see another box here and it will have another SPI ROM here, right, indicating that it doesn't have its own program. So it needs to read right? It needs to read this SPI RAM in order to configure its GPIO pins, right? But as you can see, there is no other box which is connected, so that indicates that it has its own embedded RAM, which is commonly for this EC, which is a KB9012, right? So the 4 megabyte for this one is the EC, the main BIOS, and this is for the ME firmware, right? And as you can see, PCH doesn't need to go through the LPC bus to read any BIOS. Let's go for the next architecture. Let's see what this one has in store for us. Let me zoom out. Alright, here is the block diagram. Right, as you can see, we have an AMD CPU, which is an ATI North bridge, and we have a South bridge SB600, and it is going through the LPC bus, then through the WinBond, then to the BIOS. So as you can see, the South bridge, so the CPU needs to go through the South bridge, and then the South bridge through the LPC bus, right, and then the EC through the SPI bus to read the BIOS to return the instructions back. So that is, as you can see, this is an older architecture, so it has to go through the EC. So if there is a fault with the EC LPC bus, if any fault here, then you get no display, it cannot read the BIOS. Okay, so this is the architecture in which it's going to use to read its BIOS. Alright, let's look at another architecture here. Let's go to the block diagram. As you can see, we have an Intel series CPU Meron, which is a dual core CPU. We have the Crestline, which is a GMCH, and we have the ICH. As you can see, this is SPRM, but it's not installed. This is not used. As you can see, we have an LPC bus here, and the LPC bus through the EC, and the EC, right, is managing the control, the touchpad, the trackpad, right? And as you can see, we have a SPI RAM here. So the South bridge uses its own SPI RAM, but this chip, this SMC, is an older system, older EC, so it doesn't use an embedded program, right? So you'll have to go to the schematic to see how it is going to read its program. It's normally through an SPI bus. Alright, so let's go for VCC R_, oh sorry, VCC POR. VCC _POR. It's not going. Oh, this is a compact port. Oh, SMSC. Alright, so this doesn't carry AVCC either. VBAT. No. Oh, VCC1. There's a lot of VCC1 on the board here. VCC forward. VCC forward. VCC forward. Okay, here we are. Alright, so as you can see, oops. Alright, the EC is normally on the EC BIOS. So if you go to the different section, this EC is sometimes divided into two sections. No, it's one. Alright, so we're gonna look for the SPI section. Alright, there's no SPI there. Alright, so BIOS RAM. Alright, so this is the BIOS RAM chip. As you can see, SPI chip select, which is the main selection. This is the signal that the chip will use, this EC will use, or the PC or the ICH will use to select the chip to read. Alright, so let's go to this section. This is the South bridge. Yes. That's going. This is our test point. As you can see, the EC doesn't need to go through the BIOS, so it has its own program. So this EC has its own program, so there's no connection that is connected to the EC. So looking at the block diagram, you can see that the EC has its own program inside, alright, and the EC, the salt bridge, will go through the SPI bus to read the BIOS. Right, so this EC has an embedded program. Right, so looking at the architecture, this signal is not going to the EC, none at all. Right, see, it's going to this test point and connected directly to the salt bridge. So as you can see, bootstraps PCI GNT. If PCI GNT is 0 and SPI is connected to 1, meaning if the signal is pulled up to a pull-up resistor, pulled down to a resistor to ground, or it's not installed, it's 0. If it is connected to a resistor to 3 volts, then it's on. It is default, it is the SPI. So it's not going through the LPC any at all. Right? So its default is through the SPI. As you can see here, it's through the SPI bus. See? SPI. So GNT, so if you go for the Dell here, and I type in GPIO 51, GPIO 51, sorry, GPIO 51, right? As you can see, GNT is connected to high, which is to a resistor, as you can see here. So the BBS are the BIOS bootstraps, which is, we have to find that on the schematic. So GPIO 51 is connected to high, right? And GPIO 19, let's look for GPIO 19. And GPIO 19, which is connected to another high. So that's 2 highs. So as you can see, BBS, BIOS bootstraps. So this signal is connected to a 10K resistor, and the other one, which is GPIO 51, which is connected to another resistor, which is connected here to 3 volts S. So these 2 resistors are connected to high. That indicates that its default location is through the SPI bus. So if I type in BBS, right, BIOS bootstraps, this is by default going to connect to the SPI bus to read the BIOS, to read its BIOS. Okay, the information is normally written on the schematic, but I'm not seeing it on this. So if these resistors are broken or corroded or having a fault, then you get no display because the CPU doesn't know where to go and read BIOS. Alright, so the BBS, which stands for BIOS bootstraps, and this signal must be connected to a resistor to high and another one connected to high, and that indicates its default location is through the SPI bus. Alright, if I type in GNT on this model, GNT hash or GNT by itself, as you can see BIOS bootstraps, and that's PCI underscore GNT, and its default location is through the SPI bus. It's not through the LPC bus. Alright, so as you can see here, its BIOS boot location is through the LPC bus for this one. So GNT search, alright, GNT 0. Alright, let's see, here is a GNT. Let's see if I find that GNT, the BIOS bootstraps. Alright, so this BIOS is now going through its LPC bus. So the LPC bus is where it's going to communicate here to read the BIOS. Alright, so let's look at another architecture. So as you can see here, the PCH, we have an EC, we have a main BIOS, and as you can see, the PCH is going through the SPI, then through the EC, right? And you can read the BIOS from here. But most times it goes through the LPC bus, through the EC, then the EC through the SPI bus to read BIOS. Alright, that's the formula. Alright, we have here another PCH and an LVC. So the PCH, the EC, so automatically, you know, this EC has an embedded program. So the so for this one, the EC BIOS and the main BIOS are integrated in one chip. So it needs to share it. So the EC will go through the SPI bus to read its own BIOS. When the system is on, the PCH will go through the LPC bus, then through the EC to the SPI bus to also read its BIOS. So if the EC has a failure, then it can cause no display. Okay, we have here an EC and a PCH again, as I said before, and the PCH will go through the SPI bus to read its BIOS. The EC has its own program, as you can see, so it doesn't need to go through an SPI bus, so you can know that this is an embedded program EC. We have another architecture here, which is a PCH, and we have an EC again, and the EC the EC has its own BIOS, which is the EC BIOS, and the PC has its own BIOS. So this is another architecture that you can know. This is not an embedded program. This one now, which is an EC and a PCH, it's shared, right? As you can see, it's through the SPI bus directly, not through the LPC bus. So it doesn't go through the LPC bus to read the BIOS. It goes directly through the SPI bus, right? So these are the architectures that are used by most manufacturers of motherboard in order to read the BIOS and to configure GPIO pins and so forth. So this is a very important and crucial architecture to understand, to know if the EC has its own program or it's using an external chip or it is shared. So this is a shared program, right? This is also a shared program, right? This is an independent. These are independent, right? These are shared, right? Right? This is a shared architecture where the EC and BIOS share the same RAM chip to read its BIOS and the EC BIOS. Alright, so I'll stop here. So this is a demo video. I hope you learned something, and thank you.